And then we can move on to our next speaker, who is Haoran Wang, who is a PhD researcher at the Leibniz-Institute for Photonic Technology in Jena. And he will tell us about a structured illumination extension for epifluorescent microscope systems. So please go ahead.
Good afternoon, everyone. I'm Haoran Wang, and I'm from Jena, which is like the city of optics. And today I want to introduce one of our project. It is like to do a structural illumination microscopy, which is can be implemented to all the fluorescence microscopes. So, yeah, first is the motivation. I think in all the groups there are some old fluorescence microscope bodies, and with the iteration of the microscopy methods, so everyone who works in the lab want better resolution or even super resolution. So, but it's impossible that we cannot really extend our normal or EP fluorescence microscope into a super resolution microscope. So what we need to do is whether we buy a new modern fluorescence microscope, or we can do ourselves to have some illumination extension to implement to our microscope. So that is like the money saver way how we do is really build it ourselves. And with this project, we are collaborated with two companies. Actually, it's like one from PCO from Germany and also Nikon from Japan. They kindly provide some parts for the project, and we can just direct use it and just design our extension. And as maybe lots of people working also here with fluorescence microscopy. So what is very important as illumination is a special light modulator. We want to cut out the price of our special light modulator. So we use a commercial DMD, which is designed for projector and from Texas Instrument. And we take the small mirror out and print some mount or use 3D printing, and we can implement it into our setup. So that is how the setup looks like. The whole case of the setup is using laser cutting with acrylic glass, and on it we have all the assigned holes, and then we have the 3D printed part, which will assemble our optics part onto it. We use some cheap single mode fiber coupled laser from China, and we try to avoid use optomechanics from Tor Labs, but yeah, that is like the minimum what we can do. And for the kinematic mirror mount and so on, we still need some Tor Labs part. And all the setup is mounted onto a Tor Labs breadboard, and it's inserted to the epifluorescence port from the microscope body. And for control the system, we use open source control microscope controlling hardware. It's called ImSwitch. And on the following talk from Jacopo, he will go through the detail about ImSwitch. So I will skip that section, and then I will show you some image of our with our system. So the first one is I use a 20x Nikon objective, and we see we got like better optical sectioning with our system. And then I also tried with dual color, because in the setup we can use two different laser wavelengths inside, which is 488 and with 635. So we see also the resolution here is enhanced with the setup is 1.75 times than the wide field. And with the setup, because based on the controlling from the M switch, we can do some scripting inside M switch, which is really for Python based, and we can do some time-lapse imaging. That is like the mitochondria labeled with metal tracker and excited with the 488 laser. And also, I also try to adapt step motor to our manual stage, and we can also do some sectioning with the setup. I will show the setup or the motor later. Yeah, that is the one we use from the left side. That is how we implement a step motor to the setup and try to control control our manual stage. And right side is how we have like a benchtop small incubator, which is using those 3D printing heat bed. And we have some new version of it, which was with our own designed PCB on it, and will be like a real chamber for as incubator. And yeah, at the end, I would like to thank the group of us, and it's from Leibniz IPHD, and especially I would like to thank Benedict, who is deeply involved into the this project. So yeah, thanks, and I'm up for questions.